All right, this is going to be the supplemental part 2 to the first part where we talked about all the basic terms of kinematics: displacement, distance, velocity, speed, average velocity, acceleration. We did the bowling ball Carl going up and down this cliff face. But what we're going to do now is we're going to supplement that with how you can apply this to a graph. And so I'm going to take all these same values and I'm going to apply them to a velocity time graph. And so here I'm going to go ahead and make my velocity time graph. And I know that I start off with a velocity of 10 meters per second. And I'm just going to draw an arbitrary line right here. And I know I end up with a velocity of negative 20 meters per second. And so let's just count these as all 2. So 2, 4, 6, 8, 10. And I guess I don't need to go beyond that. But down here will be negative 2, negative 4, negative 6, negative 8, negative 10, all the way to 20. All right, so if we are going to call this side velocity, I'm going to write down the units of meters per second. Also note that my graph is really big. In physics, whenever you're doing a graph, you really should do it really big because we're actually going to get some data off it that might be useful. This axis will be the time axis, and the amount of time that I use was 3 seconds. And I'm going to go ahead and go 1, 2, 3, 4, for 1 second, another 1, 2, 3, 4, for 2 seconds. I'm going to go 1, 2, 3, 4 for 3 seconds. Usually I would go all the way off to the edge of the page, but I think I might be utilizing the space here too. And so back to the original problem, our bowling ball started off with a velocity of 10 in the upwards direction. It took 1 second to stop. It takes another 1 second to get back down to negative 10 meters per second. And then another second after that, it gets to negative 20 meters per second. So off of the graph, I'm going to go ahead and put some markings down. At the beginning, we said that we started off with 10 meters per second. At the 1 second mark, we said we had stopped. So that's going to be right here, 0. At the 2 second mark, we're going to be at negative 10. And then at the 3 second mark, we're going to be at negative 20. So we're going to be down here. And so what you should notice, as my Discord goes nuts, is that this line is very, 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 very linear. In fact, perfectly so. And it should be. It should be. And there's reason for that. So we're going to take a look at what this means and if it makes sense. And so if you graph this out, the velocity of the object as time goes on, doesn't make sense that this line has a linear downward slope. And next would be, what do you mean by slope? Well, just to make sure that we're all on the same page, slope, again, is the rise over the run of a line on a graph. And so for us, the rise would actually be a negative rise because it goes down, and the run would be this way. So the rise would correspond to a change of velocity, and the run would correspond to a change of time. And so if you go back to the basic definitions, something was a change in velocity over time. That's going to be acceleration. So the slope on this graph is the acceleration. And just to double check, we're going to take a negative rise, negative 10 down to 10 to 0, and we're going to see how far we run. That's going to be a time of 1, and that gives us negative 10 over 1. Again, well, negative 10 meters per second. Don't even need this bottom part. All right, if you wanted to check units, the units of velocity are meters per second. The units of time are seconds, so meters per second over seconds, meters per second squared. So this checks out. All right, so the slope of that should make some sense. Now, if you wanted to, you can look at other things on the graph. We're going to focus on this a lot in physics. You can focus on the bound area of the curve. This goes off to infinity, so don't worry about all of this because it goes off to infinity. But we are bound by certain values here. Down here, this goes off to infinity, but we are bound by certain values right here. All right, so the first one, this is a triangle shape, so the triangle is just half of a rectangle, half base times height. And the base here is going to be a base of a time. The height is going to be a velocity value. So if we just units it right now, we're going to take a seconds value and we're going to multiply it by a meters per second value, and the s's will cancel out and we should get something that has units of meters. Well, that's kind of neat. So let's go ahead and find this area right here, and that area is going to be 1/2 the base, which is just 1, and the height, which is going to be 10. Okay, so what's half of, well, 10? That's going to be 5. So this is 5 meters. And what that corresponds to, kind of neat, is the first part where that ball goes up and stops. Now for this other part, we can take any portion of it if we want to, but let's take the whole thing. And so this whole area here is going to be a 1/2 base, which is 1, 2, times height, which is going to be -20. And so I'm going to say, all right, well, those 2's cancel out, and this is going to be -20 meters. And again, that should correspond to the -20 meters that we fell here. And so this graph is going to totally supplement and complement that diagram of the bowling ball going up, stopping, and falling down. And the total time to move would be 3 seconds. You could do a position graph, and that's going to be a little bit more parabolic in shape because we go up and we slow down and we stop and we accelerate and we get faster and our marks will be farther apart. Or you can do an acceleration graph, and that acceleration graph would just be a flat line of 10, -10 on it. And so this video will accompany the one before it. All right, part 2.